Thanks. Hi, so I'm going to be perhaps a little more specific than natural language processing, because that's a fairly broad topic. So today I'm going to talk about what happens when you throw linear algebra onto transformer columns. So I guess I am not a very well-known face here. I think basically no one knows me here. So let me start with a few words to just present myself. So I'm Timothee Mickus. I'm currently a postdoc at the University of Helsinki on the Fotran project, which is led by Jörg Tiedemann over on the Letters campus, Humanities campus, within the language technology group. So I mostly work for the Fotran project, which is about translation, and what I'm presenting here is only very partially related to that. So it's work I've been mostly doing previously. Right, so before that I was in France, so University of Helsinki, as much as pointed out, and I just finished my thesis, so this is my first postdoc. Right, and as I pointed out today, I'm just going to throw some linear algebra transformers and see what we get. So this is not work I've been doing on my own as well, so I had obviously the help of my supervisors for some parts of that, so Ms. Paperno and Jörg, as well as some other colleagues and mentor figures, I would say, such as Kate Van Winkler and Ron Vasquez, who is here in Helsinki. So, right, and if the topic is interesting to you, this would be the two major references that you can look up of papers that we have published already. So the upper one, the most recent one, is probably the most relevant to what I'll be discussing today. And the other one is just where I borrowed some of the experiments that I'll be discussing. Okay, so let me start perhaps a bit less intimidatingly than with pure linear algebra. And I'll just be starting by giving you a couple of facts about BERT, the pre-trained language model, which I suppose most of you should be familiar with, but a few refresher might be useful, and especially looking at the next sentence prediction objective that we use to train this model. Okay, so BERT, as you might know, is trained on two objectives. The first one that we most often discuss in the literature is the mass language modeling objective. So that's the one where you take a word, you blank it out, and then you train the model to retrieve what that blanked out word was. And the other one is the next sentence prediction objective. So as the name suggests, next sentence prediction is quite obviously kind of transparent. If you pass two sentences at once and you ask whether the second sentence of the input naturally follows the first in your training corpus. So to give you a more concrete example, right, so the first line here, I went to the store, I bought tofu, would be a plausible continuation. Second sentence would be a plausible continuation of the first. But if you had in your training corpus, I went to the store, penguins fly, then you probably have a corpus of shuffled sentences. So that shouldn't be technically something you flag as correct. And yeah, so just to stress, this is going to be the next sentence prediction objective is going to be what we are going to focus on for the next few slides. Okay, second point, how do we create input for BERT? So BERT is a transformer. Transformers technically require you to have like an input sequence of vectors, of embedding vectors that pass. I'll just be a bit more clear. So as I pointed out, we have two different sentences that we pass at once. So we would have my dog barks, it is a pooch, for example. And now to create a sequence of vector inputs that we can then pass on to our transformer. So that would be our sequence x1 to xn here. The first thing we will do is just take the token embeddings. So for instance, the token embedding for barks or for pooch, depending on which word you have in your sentence. So just a simple lookup embedding table. Then we add positional encoding. So positional encoding because transformers have no built-in notion of order. So these are just either defined as either they are defined as a bunch of fixed sinusoidal parameters, or they are learned embeddings depending on the variant. And lastly, in the case of BERT more specifically, we also have what we call segment encodings. which we add to words depending on to word embeddings, depending on which sentence they come from. So for instance, here we have barks that's in the first sentence, so we add it a segment encoding A that is going to signal this first sentence, whereas pooch is in the second sentence, we add a segment encoding B. And lastly, as with most language modeling tasks, you also have like some structuring elements. So in the case of BERT, we have CLS to indicate the start and set to indicate the end of a sentence. Okay. So continuing on, the third set of facts that is going to be relevant to our discussion here is about the architecture itself. So mainly that BERT is a transformer encoder. I suppose you are probably familiar with that, so I'll just be a bit brief about that. A transformer encoder is a stack of layers. So we have L different layer, and in the case of a transformer encoder, we have 2 sublayer per layer. So here you would have in orange your L different layers. Each of these layers are going to be a stack of 2 sublayers. The first one is going to be built around a multi-head attention. The second one is going to be built around a feed-forward. So it's a bit interesting to look into what's exactly in a sublayer here. So this is something that is going to be important. Around the computations that are done with the multi-head attention or the feed-forward, we also apply a residual connection. And after that residual connection, we are going to apply a layer norm. So that is just going to be a z-scaling followed by a gain, so element-wise multiplication with some norm parameter plus a bias. Okay, so that's a lot of things. Let's see if we can put things together to start making some more interesting remarks than just recapitulating how a transformer works. So this is a zoom on just like one sublayer. So you would have the computations done on that sublayer, theta, L, lambda here for that specific lambda sublayer. You have your residual connection, and then you just have your layer norm after that. So what's interesting with that is that you can see that there is going to be a path from whatever the input is to whatever the output is that goes only through additions or the layer norm itself. So if we highlight, for instance, the segment encoding, we do see that it is going to be added to a specific token. Then we can go through the residual connection and through the norm. So we kind of expect that there is going to be some sort of linear trace of that segment encoding that pops up in the output encoding. We can be a bit more formal about that. So if we have a look more specifically, that is going to be what a sublayer looks like. So we have the computation done for that sublayer here. We have our residual connection, and we have our layer norm here. We can just pull out the segment encoding because they have been defined by simply adding them. We can also expand the layer norm. So here you would have your gain parameters, which is just an element-wise multiplication. So you can always take out the segment encoding trace itself and have it put it outside of this group to just specifically isolate it and see exactly what this trace is going to bring in the output. And just for simplicity, we can lump all the rest into another term that we don't really care about. And now we end up with the output that is expressed as a sum of 2 terms, one of which is related to the segment encoding. And we started with the output, with the input, which we could express as a sum of 2 terms, one of which was the segment encoding. So by simple recurrence, you can actually carry that on through all the sublayers, and you end up with a way of highlighting specifically that your output contains an element that you can define specifically as pertaining only to the segment encoding that you pass. Or a bit more better put, because I put thought in how I wrote the slides more than I speak right now. You can say that because you have residual connection, that means that your output embedding is going to contain a linear trace of the segment encodings that it has. Okay, so that's very interesting. Why do we care about that, you might ask? And that is very obvious. So here is why this is actually relevant and why this is going to have an impact on the sort of output embedding that we expect from BERT. So this would be like a toy example. In NLP, we kind of hope that our vectors would be laid out in a way that are semantically coherent. So for instance, you would expect that pooch and dog, because they mean basically the same thing, are going to be next to one another. But now if I have a segment bias, so something that is going to push words depending on which sense they come from, I do expect that I'm going to have a very different behavior depending on which sentence a word comes from, right? Because we have a trace that depends only on the segment encoding and that varies only by a scalar, I'm going to push all the elements of one sentence in one direction and all the elements of another sentence in another direction. And by that, this entails that, informally speaking, we expect the tokens to be more easily linearly separable according to which segment encoding they actually occur in. Right, so in other words, we expect that because we added that segment encoding and because we have these residual connections, there is an impact on the sort of output embedding that we have after these models. And this is something that we can measure empirically, so that's perhaps not the best designed experiment I ever put up together, so sorry about that. It made more sense with respect to the paper I pitched it in. What we can highlight is that if we just create sets per word type of output embeddings, so we take all the occurrences of a contextualized embedding for dog, and then we just separate them depending on whether they are in the first sentence or the second sentence of the input, right? So if my dog is a pooch, this is from a first sentence of the input, and we would put it like simply compute the average for all dog contextualized embedding within the first group. And we would do the same for the second embedding. And then we can compare like one specific embedding to the average for the dogs in the first sentence versus the average for the dog in the second sentence. If the model is specifically trying to counteract the segment biases that we highlighted, we would expect the mean squared error to be roughly the same in both cases. But what we actually find is that we have a lower mean squared error when we compare dog to the average vector for the group it was taken in, rather than the other group. So if I take dog from the first sentence, it is going to have a lower MSE with the average dog for all first sentences than for the average dog with all second sentences, and so on for all word types. So that carries on pretty neatly. Okay, so just to recap that first set of experiments, what we highlighted was that residual connection introduced a trace of the input in the output embeddings. Basically, because we have a residual connection throughout the model, whatever I have as an input is going to also appear in my output in some trace form. So with that, having gone through all the gains and having been z-scaled properly, but it is still going to be something I can retrieve in the output. Okay. So let's try to have a bit more, now that this fact is now that I've pretty much made this fact clear, let's see if we can actually be a bit more thorough about what we can say regarding that. So the remark that we have about segment encoding, so the fact that it's going to appear in the output embedding space somehow, it actually is something we can generalize at a greater detail. So obviously, as I highlighted, we have this root here, and you could probably make the same case about positional encoding and word embeddings and so on. What's perhaps a bit less obvious is that the computations that are done at each layer are also going to leave a trace. So if I look at the output of theta lambda, this is also going to create a vector term that I can just consider as something like an element I add up to a current sum, right? And the output embedding is therefore going to be a sum of the computation done through all the layers. Okay, so one way we can look at that is by just grouping, like taking all of these terms and try to define a grouping of these terms that kind of makes sense for us to investigate. And so what we suggested was to group them depending on where they come from. Okay, sorry, I'm going to drink. Right. So here ET would be the full embedding, And then we have 4 different terms. The first one, IT, is kind of what we just saw. It would be the input trace. So I'm not looking specifically at isolating the effect of the segment encoding, or I'm not looking at isolating the effect of the positional encoding. We could, because that x0t vector here would be whatever input at position t that you have. But the point was more about specifically seeing whatever of the input is carried out in the output. And here we have, so just for a general reminder and to make the following equation a bit more clear, this here corresponds to just going through all the layer norms. So every gamma parameter, every gain parameter is going to correspond to a specific sublayer. For the input, you go from the first to the last sublayer. You go through all of them. And then you also have the standard deviation scaling. So these are just scalar. You just take the product because you keep adding them for all that, for each and every sublayer that you go through. Okay. So I'm going to jump directly to the F term, so the third term in this equation on the left here, which would correspond to what we have after the feed-forward computations. This is, we're not looking into it in more details right away because feed-forward have a nonlinearity, so you can't really break them down in more detail than just simply saying this is the output of the feed-forward. And that's all we can say, like from a purely linear algebra perspective, only using multiplication and addition of vectors through matrices, right? So because you have the activation function within a feed-forward layer, you can't really have a more complex output than that. And also, one thing that differs from our input trace is that now we have a sum across all layers because every single layer has a sublayer that is a feed-forward. And so every single layer is going to add a term that corresponds to the output of the feed-forward at that sublayer. Multi-head attention computation. So this is where things start to get a bit more squiggly, so to speak. So it's actually fairly similar to what we just saw in the previous slide, except that now within the square brackets, we can allow ourselves to have like a more complex vision of exactly what is happening in terms of what the input of the input of the layer, how does it translate into the output of that sublayer specifically? Because multi-head attentions can be like one attention head in a multi-head attention mechanism can be thought of as a simple weighted average of the value vectors. And so with a bit more math, you can arrive at something that is a bit more detailed than what we had for the feed-forwards. And the last term of this 4-part equation, so the CT term, is going to be basically everything that we can lump that is due to biases and offsets and mean entering in the case of your gains, and so on. So that CT term, the first line here would be simply the biases you get from the gains. So you have the bias of the gain itself that has gone through the next few one. Then you would have also the mean centering that likewise needs to go through the relevant gains of the relevant layer norms. Here you have everything related. The second line is going to be everything related about multi-head attention, but likewise you can like isolate specifically the biases of these linear projections and just like take them out. And for the feed-forward, we can specifically take the bias of the outer feed-forward. Again, with that nonlinearity, we can't really look past like simply the outer bias. Okay, so now what do I do with this funny looking equation? Now that I've broken down an embedding into 4 terms, one of which relates to the input, one to the multi-head attention computation, one to the feed-forward, and the last one to just like every constant bias in my network. I can, like one very simple thing we can do is simply plot how important they are across each layer. So here we are going to have like some measure of proportion. So that's just a normalized scalar product so that it sums to 1 across all of our items. And therefore it gives us basically a score between 0 and 1, given that they are roughly, well, it's going to give us a score between 0 and 1 in this specific case. And each different line will correspond to a different term of the equation, and we can just like graph how exactly it evolves. So for instance, the green dash dotted line here is going to be your input trace that you see clearly going down. Okay, so a couple of remarks about this graph and a couple of things that we can say right away. So the first one is that feed-forward actually seem to contribute more than multi-head attention, given this measure of proportion. So the line that corresponds to feed-forward would be the orange squares here, whereas the multi-head attention here would be more specifically the dash dot line with diamond dots. And as you can see, basically the feed-forward seem to dominate the multi-head attention, which is perhaps a bit surprising if you're familiar with NLP literature, in that, in general, when we talk about transformers, one of the things that generally pop up is what multi-head attention tend to do. And there's like a whole lot of focus more specifically on multi-head attentions and very little discussion of feed-forwards. Whereas if we actually look at the proportion, it does seem to be that we should perhaps pay more attention to feed-forwards. As I pointed out, the input trace is going to decrease across layer. That is also something that we can relate to studies about transformers. It has been shown in a couple different ways by now that if you probe a transformer at the earlier layer, you are going to have more. It's going to be easier to solve a lexical semantic task that relates specifically to the word type. Like if you try to select what is the antonym of pretty or something like that, or ugly, it's going to be easier if you actually look up at the first few layers rather than if you look up at the last few layers. And that kind of makes sense because the information more specifically devoted to this position in particular is basically almost lost at the sixth layer. So you don't really expect to have very good results with higher layers on lexical semantic tasks. And the last point that we can make is the surprisingly high importance of the CT vector. So you recall a CT vector is just basically our biases and offsets. And as we highlighted, these is just like the biases that we expect that we set up from the network. And we don't expect them to carry much meaning or to be extremely important to the total embedding. And yet at layer 11, this is basically what dominates in our vector. And at layer 12, they still remain like slightly above 20% of the total portion of the embedding. So I'm using 20% in a very loose sense here, but bear with me. So we can have a look at a bit more detail as to why this is a problem. The reason is that this CT vector is actually going to entail that our vector is going to suffer a bit from anisotropy. So the output embedding is going to have more variation in one direction than others due to that specific CT vector. And we can be, again, a bit more pedantic about that by looking at the fact that there are going to be, for each sublayer, we are going to have basically two different vectors that are going to have different scalars associated with them for each sublayer. And so that means that we can have like a linear combination of very few items. So just to get you through these slides, we can have a look specifically at the computation done in that sublayer and add them with the bias. And take the bias for these computations, the computation done by the multi-head attention or the computation done by the feed-forward. We can add those to the bias specifically of the layer norm. And that would get us like one of our two vectors that is going to vary for every sublayer, and the other one will correspond to the mean centric, right? And so here we are going to have in total a sum across sublayers of the first items that we highlighted, so the one linked to the bias done specifically at that sublayer, and the other one is going to be a sum over all sublayers of the vectors done specifically for mean centric. So we have a sum of two lambda terms, where lambda is going to be the number of our sublayers. So that means that if we have a 12-layer BERT-like transformer, for instance, we are going to have a total of 48 different vectors that are going to be, and the CT vector is going to be a linear combination of 48 different vectors. In other words, that means that we are, right, even if we assume that all of these 48 vectors are orthogonal to one another, we have at best a 48-dimensional subspace in which we express the CT vectors. Keep in mind that the full embedding itself has 768 dimensions from the top of my head. So that means that it is actually a fairly lower dimensional pocket in which the CT term is expressed. And the CT term itself is going to account for 20%, again, with my air quotes around, of the total vector. So 20% of our 768-dimensional vector is actually composed of a vector that lives in a 48-dimensional pocket. So that means that we are specifically looking at a high proportion of our embedding that is expressed in a very lower dimension than the full embedding. Right, so let's look at another couple applications that we can have with our embeddings. So we've looked at simply like graphing them across all position. Another thing that we can do is also combine that with probes, as is fairly often done in the literature in NLP. So we can just have a look at, sorry, about fine-tuning. This slide is about fine-tuning probes. It's a few slides down. So fine-tuning is just basically retraining your model a little so that it specifically fits for a specific task that you're interested in. So you would start, for instance, with a BERT-based model that you're just going to use as is, and then you train it for a few more steps on a specific task. So here we have the effect of training it for a few steps on a named entity recognition task, and here we have the effects of training the model for a question answering task more specifically. And so what we can see is that if we compare that to the BERT base that I just showed you previously, and we do see that there are like very different behavior that seem to emerge. The first one being that the feedforwards at the very last layer tend to be a lot different in the sort of things that they do as compared to the BERT-based model. Another is that they also seem to strongly counteract the bias term CT that we highlighted. Another thing that we can do, so these graphs are actually taken from the same set of from the same data sets, so same sets of embeddings. So we can simply correlate these proportion measures to see how exactly the measurement that we have differ from the fine-tuning case or the base case. So that will be our first graph here. We compare the BERT base to the NER fine-tuned model. And here what we can see is that the majority of the changes in terms of the proportion of the output embedding occur specifically in the higher layers, right? So given that we are just basically pairing up vectors in the original case and the in the original non-fine-tuned, just pre-trained model and the one we have fine-tuned, what we see is that there's basically zero correlation as to how the multi-head attention behaves between the case of our base model and our fine-tuned model. We can do the same with the BERT encased model, so the base model and the one that is fine-tuned on QA, on squad specifically. And here we do see that we have, like, again, a slightly different pattern, but overall, most of the changes seem to occur in the latter layers, and only the multi-head attention itself seem to be highly modified in the case of the fine-tuned quad model. And we can also see that the changes are very much task-specific, because if we correlate the two models, then we again have the picture that shows us that the correlation is much lower between the proportions assigned to all of these vectors. Okay. Right. So the big picture of that is that we have one way of showing where fine-tuning actually changes your model, and that seems to be mostly the upper layer, and in certain cases also in your attention head throughout the models. Right. So this is just a brief parenthesis. How am I doing on time? Okay. I'll just go very quickly through that. Thus far, I've only spoken about transformer encoder. This is obviously something we can also do with decoder. And that has been one of the things I've been doing within the Fotran project. And it's more specifically, here you would have instead of having stacks of 2 sublayers, you have stacks of 3 sublayers, where one is self-attention and the other is attention to the source. And so you would just like add corresponding terms for these various layers and define them exactly as you would the HT layer. In the base case, here you would have 2 different ones for these different stacks. And you can use that then to have a look at how the model behaves. You might throw a different output at it. So this is, for instance, where I simply take a pre-trained existing translation model and look at what happens when we vary the data set of the inputs that we have. And what we can say is that it's mostly the attention, most of the variation seems to happen specifically within the attention mechanisms here. So I don't have the confidence interval, sorry about that, but the confidence intervals seem to be much greater in the case of the attention terms than they are for the feed forward and the constant and input trace. And another thing that we can do, and this is like, again, more work in progress for that, which is like comparing similar model on the same input, but with a variation. So these are 3 translation models. The first, the one here on your right, if I'm not mistaken, yes, that should be your right, is going to be a multilingual model to English. This one is a Romance to English, and this one is a French to English. And what we can see is that so the source and target seem to behave quite differently in the case of the multilingual model than in the case of the Romance or the French language. Right. So very brief parenthesis just to say that what I've discussed is also going to apply to the decoder model, but we can obviously do a bit we can actually do that, right? Right, so the last point I'll be discussing before perhaps stopping for question is going to be about trying to combine this decomposition with what we call classifier probes in NLP. So just like a simple linear classifier that you learn on top of some representation to try and see what you can extract from that. And mainly with the question of trying to see whether the output of one specific sublayer still carries on the same information that you could retrieve from the output of some other type of sublayers. And we're going to look at worst instance ambiguation using the SEMCORE dataset for those who are interested in the details. And we're going to test all combinations of possible terms exhaustively. So the I term on its own, the I term plus the C term, the I term plus the F term, and so on until we have the full embedding. And that gets us right the following table. So this is color coded. Dark red is the worst performance, whereas dark green would be your best performance. And I am very sorry if we have colorblind people here. I really hadn't thought of that when doing this graph. So we have, I'm just going to discuss the classifiers that you have on the bottom here. There's also a KN and baseline if you're interested, just for comparison. So that's 5 runs, individual results on 5 runs with hyperparameter tuning and everything. This would be the average of the 5 runs, and this would be your standard deviation. And really, there's a few things that we can highlight. I think the most interesting one here is that actually when you have the feed-forward output within that scheme, this is when you perform the worst. So if you drop the feed-forward, this is this column here. Whereas, sorry, if you drop, I'm a bit tired. If you only keep the feed-forward, this is this column here. And cases when you, on the other hand, cases when you drop the multi-head attention, which is going to be the bulk of the computation done by the model besides the feed-forward, this would be this column here. And if you look into it into a bit more detail, what you do see is that it's systematically better to not have the feed-forward attention rather than not have the multi-head, not have the feed-forward sublayer, sorry, than have the multi-head attention. And in general, the only thing that performed worse would be the CT term and the I term, which you don't really expect to perform that well because it's a word sense ambiguation where you expect context to be relevant. And neither of these things actually tend to vary a lot by context. They are fairly fixed. Okay, so I'll just conclude a few words on that section here, and I'll just skip to the conclusion after that to have some time for question. So what we highlighted here is that if we just decompose the transformer according to the linear factors that it contains, we do have like some explanation as to why do we find anisotropy in the output embeddings. We also saw that position-specific information, so the information about the word that you have at that specific position, tends to vanish across layers. So it does question whether the output embedding at one position has actually anything to do with the word you are considering. So if you're taking the embedding for cat, or you within a sentence like I have a cat, are you actually taking something that says something about the word cat or not really? Right? You don't really have a strong connection with the position and the corresponding output contextual embedding. Fine-tuning, as we highlighted, mostly impact upper layers, which is also something that we know by just like looking at where the gradient goes when you fine-tune the model, but it's interesting to see that we can find it in other ways. And feed-forward are also like fairly prominent in the output model, but at the same time, they seem to be detrimental on certain tasks when you test them. Okay, I'll just skip this because this is obviously very interesting, I think, but it's still work in progress, and I'd like to have some time for question if there are any. So yeah, so just skipping for conclusion. So I think I made a case that because you have residual connection and the layer itself is mostly defined in a fairly linear way, you actually have just simply looking at what these linear connection entail, residual connection entail, actually brings sheds a lot of light on what the model, how the model is behaving and what sort of things it's doing. Right, and we can also have a more specific targeted way of looking at specific sublayers, which isn't something I've been doing here, but that you could definitely do with this sort of decomposition I've been arguing for here. What's really interesting is that this also conjugates very well both with a parametric tool like classifier probes, and also with like simply taking measurements and looking at them like using correlations and stuff like that. So it's fairly agnostic as to how you want to use it. And yeah, so there's a few possible next steps as to where to take that. I'd be extremely interested in looking at other way of grouping the terms. One thing I've been looking into is whether you could group terms depending on which token they come from, rather than which sublayer they come from. And there's some very messy things involved due to the feed-forwards that you can't just like readily break down. And also compare these sort of groupings with what humans would judge is relevant or not for the semantics of within optics. I'm also interested in looking at what would happen across training. For instance, is it always the case that the input trace vanishes, or is it something that the models tend to acquire by themselves across training? Okay, I think that would conclude my presentation, and I'll be happy to take questions.
Thanks, Timothée. So, are there questions here? So, if there are questions in Botaniemi, you can be ready as well to ask it and write in the chat if you want. So, are there questions? Yeah. Okay, I have a small. Sorry.
I was going to jump in. In the beginning, it seemed like there was an example that it looked like the feed forward term was closest to the output embedding in general, and then in the more comprehensive table you showed towards the end, the feed forward term was sort of the.
So you're thinking, sorry, about this table here,
yeah,
versus, sorry, this graph here.
Yes, exactly.
Okay, so this is just breaking down your embedding depending on the scalar projection onto the full embedding, so that you get like a general sense of how codirectional and whether they have similar norms or not. Sorry. And so here we're just like purely looking at the geometry of things, which is not exactly surprising that you have like such a prominence of feed-forward layers, because we're taking as reference the full embedding for that layer. So the one you get like basically right next after having run through the feed forward and then having gone through the game. That would be the end of the game, right? So that's purely about the geometry of the embeddings and purely looking at how the feed forward itself, how much of the variation in my embedding can I explain due to the feed forward term.
Right, and not necessarily how easily separable it is.
Right. Whereas here, this is basically just a table that looks at the performance of a classifier on a specific task, and that task would be word senses evaluation. So this is technically a two-stage multi-layer perceptron with one specific head per ambiguous word. So if you have a word like Thai, it's going to have to share the first layer of your two-layer perceptron, and the second layer is going to be specific for the word Thai. And it will be simply a multi-class problem here between possible senses of Thai. So Thai as a verb, Thai as a draw in a game, Thai as a piece of cloth that you wear around the neck, and so on. And here what we see is that when we add the feed forward term, or when we don't keep the feed forward, well, if you include the feed forward term, you actually get worse performance than if you don't. And so that is just telling you that whatever these 40% of the output that correspond to the feed forward are, they're not very well aligned with solving the task in question. Like they contain stuff that tends to be more noisy than useful for the task of word sense migration.
Thank you. Yeah.
Do you think that the word sense that the feed forward part is detrimental for the word sense ambiguation because of the type of information that might be stored in that from the context versus where that it might actually be at the attention?
Right. I strongly suppose that something of the sort is going on. So there's a lot of literature on 5 papers on literature about feed forwards. And they seem to generally suggest that feed forwards are more about updating your output probability for the mass language task.
Yeah.
Which is useful, but not as aligned with word senses ambiguation as having like a pure average of all possible words in a sentence, or as you would have like right next to the output of the multi-head attention.
Yeah.
Yes.
So, have you, did I understand it correctly that you have tried already with, let's say you have sentences with dogs and see how they token of the word, how does these numbers of the graphs can they change for different types of words, if that makes sense?
No, I haven't really looked into that yet. That's also something that I've been wanting to, more specifically within part of speech would probably what would make sense, in that you expect the semantics of a verb to more depend on the sort of object and subject it has, whereas the semantic of a noun should be probably a bit more constant. That's definitely something I've been wanting to look into, and that's also something I kind of wanted to suggest about comparing with human judgments, just to see whether something like the input trace that you have for a word is going to be correlated with how stable the meaning of the word is across different sentences. Like that would be one way of looking into that, I think.
So on Botanimi's side, are there some questions? Emily?
Yeah, so can you hear me?
Yes.
I just have a few comments. So can you go back to the slide where you show the importance?
This one?
This one. For example, this one. So these error bars are computed over different. Okay.
Yes. I took 10,000 words from the Europar corpus, which is technically not within the training distribution of BERT. And then I just simply computed the importance of each of the term for every token I would embed in these 10,000 sentences. And then the error bar would correspond to one standard deviation with respect to the average. And here I just plot the average.
I
So-
see that this trend could change if you just consider different BERT models, like different runs.
That is also something I've been needing to look into. It turns out that training a BERT model from scratch 5 times just to get different random seeds is expensive and complicated. And this is why I haven't really been doing that yet. Definitely there is like some need of looking how stable it is. I plan to do that more specifically with machine translation models, where it's also perhaps a bit more relevant to my current postdoc as well.
Yeah. Cool. So there is also there is one paper that analyzed the power of transformers, and one of the takeaways is that the attention mechanism is somehow proportional invariant because it's kind of a weighted average, and they claim that we need the position encoding to make it Turing complete in terms of recognizing languages. But in your, do you know this? Do you know this work?
There's been the one I'm thinking of that might fit the description would be variation on the who was that? That might have been Milo Otts who worked on that or something like that. There's been a few suggestions as to how to modify attention so that it also factors in positional encodings. So there's 2 ways of doing that. Either you would add like some sort of positional encoded matrix to the value vectors, or you would add that to the way you compute weights in your multi-head attention based setup, right?
My point is that so you basically show that the importance of the position encoding, it's not, as we go like over the layers, it becomes less and less important, right? It's kind of interesting to see this.
Yes, so the information specific to that position, so the input vector that we get for that position is more or less lost after a few couple layers. It's still important to note that the computations that you do on one layer depend on the computations that you do on the previous layer. So it's not like a complete, like if you just look at the computation transitively, then you still need to have these positions to get something with the output. But it does seem that the information specifically about the linear dependency of the positional encoding itself is more or less lost after layer 6, yeah.
I see. Okay, yeah. So congrats on your work. It was really nice. Thanks.
Okay, so if there is no more question, I propose to thank Timothée.